Hello. So one more convergence test for right now. We're going to take a look at what is called the root test. So we just did one on the ratio test. This one has a similar kind of structure to it. So let's just go ahead and work this out. So here's our root test. Let me state it. Again, I'm not going to do a proof for this one. The proof is pretty similar to the ratio test. Both of them, if your series does satisfy the conditions of their test, it's easy to make a comparison to a geometric series. So yeah, the setup for these things lets you make a comparison to a geometric series, and then if you know that your geometric series has a ratio less than 1, that's where the limits less than 1 come into play here. You can prove it, but we're not going to do that. I just want to make sure we know how to use these rules. So the root test is as follows. 3 parts again. If the limit as n goes to infinity of the nth root of the absolute value of the terms of a series are equal to L, which is less than 1, then the series is absolutely convergent, which means it's therefore convergent. Okay, so very similar to the ratio test. We take a limit of something and look at its value relative to 1. So the other 2 parts, if the limit of this thing, this nth root of the absolute value of the terms is equal to L, which is a number which is greater than 1 or infinite, then the series is divergent. Okay. And then finally, the same problem happens if the limit as n goes to infinity of the nth root of the absolute value of the terms of the series is equal to 1, the test is inconclusive. Meaning we don't know. You can have a series whose limit in this way is 1 that diverges. You can have a different one whose limit is 1 and it converges. So you can't tell. You have to find some other way to get at the convergence of the series than this test if the limit turns out to be 1. So we're just going to do 2 examples for this root test. Let's do it on new paper. So let's start with the series. Let's consider the series n equals 1 to infinity of 2 to the n over n to the n. Okay, so this is pretty typical for the kinds of things when you'll want to use the root test, in that it has powers of n, right? It has exponents, sorry, not powers of n, it has exponents that are n, right? Because the root test will get rid of this, okay? So let's just do a little bit of work here just to make it even clearer using my rules of exponents. This is 2 over n to the n. Okay? So if we use the root test here, we can say the nth root of the absolute value of a sub n is equal to the nth root of 2 over n to the n. So if you take something, oops, I forgot my absolute values, though it doesn't really matter in this case because everything's positive. We'll do one in a second where they're not. Or I guess we won't. We take that back. So if we take something to the nth power and then take it to the nth root, we end up back where we started. So this thing just looks like, or since this is all positive, 2 over n. So now we take the limit as n goes to infinity of the nth root of the absolute value of the terms of our sequence, and we get the limit as n goes to infinity of 2 over n, which is equal to 0. Okay, And now we refer to our root test. We took the limit, we got a number that was less than 1, we got the number 0, so the sequence is absolutely convergent and therefore convergent. So, therefore, the sequence 2 to the n over n to the n is convergent. Okay. All right, that's it for that one. I will point out this series here, you could also, and this goes for anything, I'm just noticing it right now, this would be a pretty easy one to also prove as a comparison to, say, a geometric series. As soon as n is bigger than 4, for instance, then this is less than the geometric series 1 over 2 to the n, which we know converges. And so then we get that comparison test convergence. So this is one way to do this one. There's often other roads to get these. Okay, but nothing wrong with what we did. We found a convergence here since the limit was equal to 0. All right, let's do one more example. Let's do an odder looking series. We have n equal 1 to infinity of the nth root of the square root of 2 minus 1 to the n. Okay. Again, we see that we have an exponent of n. This is a good time to think about trying the root test. So let's take the nth root of the absolute value of these terms. We get the nth root, the absolute value of the nth root of 2 minus 1 to the n. Okay. And again, rules of absolute value, I can move this thing outside, and then I'm taking the nth root of something to the n power. This will, since it's all positive, everything's going to go away nicely. We end up with the absolute value of the nth root of 2 minus 1. The nth roots of 2 are always bigger than 1, right? So this ends up just being, I can drop the absolute value and get this. Okay, and so this is the thing I need to take the limit of. So we're looking at the limit as n goes to infinity. Let's maybe write this as 2 to the 1 over n minus 1. This is equal to the limit as n goes to infinity of 2 to the 1 over n minus the limit as n goes to infinity of 1 using our limit laws. Well, we have to use the limit law when we've got continuous functions. We can take the limit can pass inside, and that the limit of this 2 to this expression is, the limit of 2 to this expression is the same as 2 to the limit of this, right? And it turns out the limit of 1 over n is 0, so 2 to the 0 is 1. The limit of a constant is a constant, we get 1, we get 0. So again, we've got a limit of 0 in this case, and we know now that our series converges. Okay. All right, that is it for the root test. Thanks, everybody.